Hey guys, this is Karan here. I live in Saudi Arabia, study 9th grade in Yambo International School. Today in this section we'll be talking about static electricity, as you guys can see it up on the board. Now, sometimes on a dry day, you walk across the carpeted floor, okay, and you feel the shock as you touch the doorknob, okay. That's our topic on how does it happen, okay. Now what you will learn after I stop talking and we saw some examples, what you will learn is, the first thing that we'll learn is three particles that are in the atom, or that three particles that make up the atom. The second thing that we'll learn is define the electrical charge, apply this fundamental rule of charges. The third thing that we'll learn is describe the factor which affects the electric force, calculate the electric force between two charged objects. Doesn't matter if it's negative charge or positive charge, okay. Compare and contrast the electric force with the gravitational force, which we learn in fundamental physics. So like I told you, fundamental physics is like a base of advanced physics. So the fifth thing that we'll learn, okay, is describe which types of materials are conductors, or which type of materials which are insulators. Okay, the last thing and the sixth thing is describe and calculate electrical fields and electrical potential. Okay, not electrical potential energy, just electrical potential. So let's just start off with what makes up the atom. Okay, now all the matter in the universe, okay, all the matter in the universe has made up of tiny little particles known as atoms. Now, as you may have already know, atoms are made up of smaller subatomic particles called protons. Okay, three particles. The first is protons. The second is neutrons. Third is electrons. This three subatomic particle over here makes up an atom, okay. So this over here are basically subatomic particle. Okay, now let me just tell you on how does the atom actually look like. Okay, now this is something that is used for basic understanding, and scientists nowadays have configured new type of atom which is more advanced, but just for the understanding skills, I'm gonna do the way people used to do it. Now how it actually looks like is, you have the proton here, the positive charge, the neutron here, neutral charge, neutral charge over here next to it, and the positive charge over here. So this is actually the nuclei. We discovered the nuclei of the atom. Now here you have negative charge particle, which is okay. Now this is basically the atom. This is how an atom basically looks like. So this is basic model of an atom. Electrons are negative, or the electrons are orbiting the nuclei that consist of positive charge, which is proton, neutrons, which is neutral charge. So protons and neutrons are found together in the region in the center of center, which is basically called nuclei. So let me just write it down. Nuclei. So this part over here is basically called nucleus. Nucleus of an atom. For our purpose, we'll use this simplified model, okay? We won't use the advanced model because it's not our critical to our understanding here, because it's not too, it's basically not that much. You cannot understand that much out of that diagram. Here you can actually understand something and get the knowledge of it. Now protons, let me just talk about protons, which is positive charged particle. Okay, protons are much larger and more massive than electrons. So this particle over here, this and this, are more massive and more huge particle than the electrons over here. Electrons are negative charged particles. Okay, neutrons in this case is approximately the same size as proton. So we can, since we say that the protons is massive and huge in size, we can also say that neutron is approximately huge in size as well. And likewise, we can also say that neutron is a massive in size as proton over here. As we stated earlier, that all the matter is made up of atoms. The proton from different atoms are always identical. So suppose you have, since we said anything is made up of atoms, we take a substance here, okay, and that substance has a same diagram over here, and it has some protons, okay, and this object, okay, has protons over here. So no matter what type, this is type A, this is type B, okay, substance type A, substance type B. So what happens is, if you look at the substance type A atom, okay, and you see the proton and you compare it with substance type B's atom, okay, you will find out that this both proton is what you are actually looking for. So basically they are congruent to each other. They are identical. Likewise, electrons, okay, the electrons over here and the neutrons, are identical to this. No matter what type of matter it is, no matter which kind of atoms they come from, okay, electrons and neutrons are always going to be the same with another object. Okay, so let's go ahead and move on. Now we'll move on to electric charges. Okay, so let me just go ahead and erase the board. Not gonna erase this because that's the main concept here. So what we are trying to do is, now we are studying electric charges, and slowly and steady we'll move on to a little hard stuff. Okay, but I'm just gonna give you an introduction to basic stuff to actually understand the hard stuff. So now we talked about what actually makes up an atom, and we actually understood what is atom now. Now let's talk about our next part called electric charges. Now one of the unique characteristic of subatomic particles over here is the property of electric charges. As you guys can see, proton has positive charge, electrons has negative charge, neutrons has neutral. Okay, now scientists observed that electrons were attracted to protons. Okay, electrons were attracted to protons just because it's opposite charges. So you can say when you have opposite charges, it attracts, and when you have similar charges, which is electron does not attract to electron, okay, it repels it. Now the property that caused the attraction and repulsion, okay, so when you have negative charge over here, electron over here, and proton over here, what it does, it attracts each other. Now likewise, if you have proton and proton here, neutron and neutron here, electron and electron here, it won't attract. What it does, it would repel from each other. Okay, this guys over here would repel, and here this guy would attract each other. Okay, that's what I'm trying to say. Now, since they have the property of attraction and repulsion, okay, now scientists they need to have some kind of charges, because without without those charges, they wouldn't have this kind of properties, which is attraction and repulsion. So this type of charges, when attraction and repulsion happen, it's basically called electrical charges. Okay? Now they need to distinguish some kind of charges given to this object. So they need to have some kind of electric energies in them to basically attract or have those kind of properties which I just showed you over here. Now neutrons, let's start off with neutrons, because I already talked about those. Protons, which is positive charged particle, okay, but we'll learn some in deep briefly, okay. So neutrons is what we are talking about. Neutrons is basically neutral. Okay? Neutron has no charge. Neutron doesn't have any charge, and they are electrically called neutral. Okay? This over here has no charge. And electrically, it's called neutral. Okay? Electric energy is considered a fundamental property of matter. Now the positive electricity charge of the proton here is equal in size to the negative electric charge of an electron. So here the proton is actually equal in size as the electron over here. And what happens is, if you have many protons over here, and you have less amount of electrons, what happens is the particle that the substance you're actually taking is going to be net positive charge ion, okay? And that's what I introduced you to the ion. Now let me just go ahead and erase the board to actually make you guys understand what I'm actually talking about. So if you have two positive charged, okay, and just one electron, what happens is this cancels out with each other, and what you're left with is this. Now then this is actually the net change, so you guys can check. Now we already learned in our fundamental physics that net means whatever you're doing, addition or subtraction, whatever you're doing, the final answer is actually called the net. Okay, and it's represented as a symbol of sigma. Okay, so if you were to have more electrons, the net change would the substance you're actually taking, and which has the more electrons in it, the net change would have more electrons in it. So atoms such as this, okay, which carries net electrical charge, so any type of charge, here we talked about net positive charge, you can also make this neutral, and what happens is this and this cancels out, you're left with is an electron, so the net charge of this substance would be a negative charge particle, but which this net electrical charge particle is basically called ions. So let me just write the definition of ions. Ions are basically atoms that we talked about, atoms such as this over here, which carries net electrical charge is what is called ions. Now, how are ions formed? Now, how are they being formed? Now, ions over here, ions, are formed by either adding or removing electrons. So basically here you just have more electrons in it. You don't have protons. Okay, so you can either add an electron or either remove an electron by adding one proton. So if you add one proton to two electrons, what this is going to do is remove one electron and it's going to cut by itself. So here you have two electrons and one proton. That's what I'm talking about here. And what happens is this cancels out with the electron over here. What you are left with is the net change, which is electron. Now that's basically what's ion, okay? And what you're left with is net change, negative change, okay? Negative change of an ion. Now remember, from the fundamental physics that we talked about is that energy was being conserved. Now here, something is being conserved that I'll tell you in just a moment. Now what's being conserved is that the electrons over here cannot be created nor being destroyed. And from the energy law, we can always conclude that energy is never created nor destroyed. Isn't it similar? Now energy, we say that it's conserved. So electrons here are in the same way. We see that the matter over here, the matter here, is conserved in much the same way as the energy was being conserved. Now, note that if it is very difficult to add or remove proton from a nucleus of an atom, okay? We'll talk about this in our discussion on nuclear physics. So let's move on. And here I will be introducing you to the electric forces. So let me just draw a diagram of it and let us talk about it. Now we know the basic concept, so we are actually moving on to the hard things here. So what you have is basically what we are talking about is electric forces, and I'm going to be introducing you, so this is going to be intro. Okay, now the diagram that I need to draw to you for you guys to understand is basically you have a proton, which you should know because I already drew this. Proton and electron are being attracted. Okay, and then if you have proton and electron, what happens is it repels. So this two guys over here repels, and this guy attract. Now, as noted, one of the unique characteristic of electrical charges is the fact that they cause attraction and repulsion. Okay, we said that. This implies that a force must be acting on these guys to make these things happen. Now, we can say that if you put proton over here and proton over here, they're basically going to attract. Now what happens? Repel. And proton here and electron over here, what happens is they're gonna attract. So they can, the forces that are using to attract or repel are being held at long distance. Now, meaning it acts over a distance which is pretty huge, or it could be small distance, it could be long distance, but here, just in case we are in this topic, we'll be using long distance as a force acting. Okay, so the electric force acts between two objects, as you guys can see. So it doesn't matter if it attracts or repels. Now, two charged objects doesn't have to be in contact in order to experience this electrical force. Okay, so they don't have to be stick to each other. They don't have to be close to each other to make that happen. Like this over here, they're close to each other. These markers are close to each other. They don't have to. This subatomic particles over here, they don't have to be next to each other to make that thing happen, to make the electric force work. Now here we'll be talking about fundamental rule of charges. So what we are learning is fundamental rule of charges, and it's something that is very basic if you played around with the magnets. Okay, now the fundamental rule of charges states that like charges repel each other, one another, and unlike charges attract each other, one another. Therefore, two negatively charged particles or objects would try to push each other apart, or two positively charged particles or objects would also try to push each other apart. But only one negative charged particle and one positive charged particle, okay, object, which is in an object, what happens is they will try to attract each other or try to pull each other closer to them. Okay, now here I will be talking about Charles Coulomb. Okay, now he was a physicist who performed numerous experiments with electrical charges during late 18th centuries. So for a groundbreaking field, he was very intelligent. Okay, so whatever we do, the unit of electrical charge will be named after this. So whenever we have an electrical charge, let's say 6.23 times 10 raised to the 12. Okay, you put C next to it, like we put joules next to the kinetic energy. Okay, so we get 32.3 joules of work done. Okay, or kinetic energy. Here, if you have an electrical charge, you put C next to C. The electrical charge would basically repel this over here. Now, however, I want to make this video tutorial a little bit more interesting, because now whatever I talk about is basically introduction to it. Now what we'll be talking about is getting deep into it, see this kind of perspective by physics point of view. Now let's look at this points over here in physics point of view. Now we talked about protons, okay? Now we actually need to know the weight of the proton. So how do we know the weight of the proton? And it's something that I will give you without proving it, because they measured it, the scientists. So the fundamental unit for the charge, a proton, is basically 1.60 times 10 raised to the negative 19th. And remember, like I told you, you put C next to every electrical charge. So you put C next to this, and what this is the fundamental unit charge for proton. Okay, likewise, you can put over here, what's easy, now what I'm going to give you is the mass, the electrical charge for electron here, and it's pretty easy if you know this over here, because basically what you do is just add the negative sign over here and make it, and it's the same thing. And this is the charge for electron, single charge, single electron, which is single. Okay, that's important. So let's move on to the electrical forces of Columbus' law. Now he lived till he basically experimented since 1785 to 1789. Okay, and he did much of the work in his study lab, or what you can say, and basically what he did is studied about electrical charges, and he experimented. Now what he found out is that there has to be something in relation between forces, what acting on it, and the charge. It depends on the charge what the forces are, and it depends also on the distance. So now taking this relationships, okay, and basically what he said, that he said the force is proportional, okay, to the this. Now this is basically inverse squared relationship, okay, and basically R is the separated distance, okay. Now what I'm going to be talking is about how the units are being put in an equation, because when this units just pop off you, just come to you, what happens is many people get confused. So before moving on to the equation part, I want to actually tell you guys what the symbol represents. Now force we know is F, you just have to write F, and the force is always in newtons. So what we need to remember in this section is the charged particle, you put C after it, a capital C, after Newton, which is after force, you put Newton N over there. Now let's go ahead and talk about it. Now for the force, you express force as F, we all know that. Now charge comes in over here. Now this is what we need to know. The charge is basically represented as Q, okay? The distance, which is separated distance, is basically represented as R. Now the relationship has to come to know, this is the Columbus law. Now the electrical force is equal to constant of the product of two charges divided by the distance between the charge squared, okay? So what I'm going to be saying is introducing one more, and K basically is known as electric force, okay, which is constant. And K is equal, and this is something you always need to remember, K is always equal to 9.0 times 10 raised to 9. This is basically easy to remember, because if you remember 9, all you need to know is the exponent is 9 as well. That's basically it. Now 10 raised to 9, and that is Newton times meter squared divided by Columbus squared. Okay, so this is what we need to know before we move on. So let's actually move on and to the equation part. So when you actually get an equation over here, we'll solve one problem on it, just to know how the equation is being used in static electricity or electrical charges. So here you have the Columbus law. Okay, that says that the force of electric force is actually equal to the K times the quantity 1 times quantity 2 divided by the radius, which is being squared. Now let me just go ahead and explain you all this. Okay, like I said, F is representing the force. Okay, K is representing the electric charge. Constant, and we all know K is always equal to 9.0 times 10 raised to the ninth, okay? Exponent, which is 9. Now, the R is basically the distance between those objects. Okay, and this two over here, what it says is the electrical charge, electric charge of the object. Now let's go ahead and solve an example to actually get the idea of what I'm talking about here, and how the most important thing, that how this equation over here is basically used. So we know that the equation, now the problem basically says, and you better pay attention to it, or actually it would be up on the board over here. Now the problem says that two charged objects are placed 2.3 meters apart, as shown above. Okay, that's all it's trying to tell us. And if the question doesn't appear, okay, don't get 2 tenths, because I'll be writing down. Now basically what it's saying, because I have to write down every single thing because it's a diagram. Okay, now here you basically have two basic substance, okay, charged objects, as you guys can say. Now the charge of this object over here is basically 6.8 times 10 raised to negative 8. You put C after it, okay, and the charge of this object is negative 3.7 times 10 raised to negative 8. That is, okay. Now what's it saying is the distance between this object is basically 2.3 meters. Okay, the distance between it is 2.3 meters. Now what is the electric force that is acting between these two objects? Now how would you calculate that? Well, use the equation that we just talked about, which says the force of electric is equal to K times Q1 times Q2 divided by the radius squared, or the distance squared. Okay, so the force of electric, how it would look like, is basically K, we know, is 9.0 times 10 raised to the 9th times Q1. Q1 is the charge one, so 6.8 times 10 raised to negative 8 times the Q2, which is this over here. So we do negative 3.7 times 10 raised to negative 8, okay? And all of that divided by the distance, which is 2.3, and you square that. So when you do that, you get your answer to be negative 4.28 times 10 raised to negative 6. So the answer, the final answer, is basically negative 4.28 times 10 raised to the negative 6. And since its force is always in Newton, and I don't think that we need to go over this because we already talked about this in our fundamental physics, okay? Fundamental physics volume. So the electrical charge is this much between those two objects, and now we need to know that if it's attracted to each other or repelled to each other. And how exactly do we know that? Well, since we know that protons are positive and electrons are negative, look at the charge over here. Since this is positive over here, all you look at this over here. Since this is positive, okay, and this is negative over here, it would actually attract because charges are different. Since the charges are different, they would basically attract. Okay, so let's move on to electrical forces and what's called the gravitational forces, which we talked about. Now I'm going to be telling you what things are similar in it, what is the major difference between it, because if you look at this equation, it actually looks like the gravitational equation that we talked about in our fundamental physics. So let me just write it down if you don't know the gravitational equation, which Isaac Newton invented, the universal law of gravitation. So we'll talk about similarities between those two. Now, so the first thing, the force of gravity is equal to the gravity times the mass 1 times mass 2, all divided by the radius squared. And the equation that we talked about right now is force of electricity is equal to the K times the Q1 times Q2 divided by radius squared. Now it looks similar to this. It's basically distance, okay? So both the electrical force over here and gravitational force are long range forces. So the similarities is both are long range force. Long range force. Okay? Meaning they act over a distance. They need not to be direct contact, so they don't need to be in direct contact. So both of these are capable of producing acceleration to an object. So what these are capable of is providing acceleration to an object. Okay? So another important thing that we'll talk about this is basically the masses. Okay, here it's being used mass 1, mass 2. Here we have electrical charges 1 and 2 of another. Now it's basically both are using inverse laws, okay, because you are squaring the distance. Okay, so both are using the inverse property. Now what the difference is that if you don't know this, okay, this over here charges, we say that it may attract or repel. Here it only attracts, okay? So the gravitational universal force only attracts the object. Here the object can be attracted or it can be repelled. Now that is the most important difference, and the second difference is that the gravity that we use over here is basically the gravity which is equal. The gravity that we use is gravity is equal to 6.67 times 10 raised to the negative 11. Okay, here the K is equal to 9.0 times 10 raised to it's 9. There, okay? So basically, what the difference between those exponents over here is basically what I'm trying to say is the difference is 20. So that's a huge number. Okay, and all it means is that if you have different exponents, the number is going to change as well. Now if you are given a number, okay, a huge number, what you need to do is first convert it into scientific notation, which we did over here, and then we found out the difference. So that's the major difference in this object. Now let's go ahead and talk about the conductors and insulators. What are actually conductors and insulators? Now conductors, first recall in section 1.2 that we talked about net electrical charges, which it results that in gaining or losing some kind of electrons to it. Okay, certain types of material that basically makes the electrons transfer freely is what's called conductors. So let's go ahead and write the definition down. So conductors, we know that when the electrons are moving freely, that's in that substance is called conductors. Whatever that substance is that is making the electrons move freely, it's called conductor. Okay, now the conductors may be such as metals, for example. So the example for a conductor is basically metal, type of metals. Okay, other substances, what happens is, such as rubber or plastics, what happens, the electrons the substance is not letting them move freely. Okay, it's harder for them to move around those substances, which are basically called insulators. So when the electron has hard time moving around, is basically called insulators. Okay, and for example, like I said, rubber is one example, then it's plastic. Okay, and or there's one more example, which is glass. Okay, so all it does is it makes the outer electrons, remember that electrons are moving in the outer area. Okay, so it makes the outer electrons they don't allow the electron to move freely. Okay, and that substance is called insulators, and the substance which makes the electrons, the outer layer of electrons, to move freely is basically called conductors. Now we have something that is called semiconductors. So what semiconductor is, that involves these two properties. Now when a substance is involving these two properties over here, is basically called semiconductors. Okay, and the example for that would be a silicon. Okay, and it's a pretty good insulator because it's pure and good conductor, because when the small impurities are added, it basically makes the electrons move freely around those substance next to it. So now the thin layer in the semiconductors are basically called transistor, but we won't move on to the transistor. Let's move on to something that is called superconductor. Now, the thing that is called superconductors is basically who has good quality of making the electrons move very faster at a faster rate. So when the electrons of the outer layer of electrons are basically moving faster, okay, faster than conductors, what they're known to be superconductors. Okay, so it makes them move faster, but what happens is it doesn't always make the electron move faster. It happens only when the temperature, the substance is, whatever the substance is, when you put that substance into low temperature, that's when the electrons, the outer layer of electrons, are basically moving freely. Okay, so it's basically working at very low temperature. Okay, so let's move on to how do objects are being charged. So let's go ahead and erase the board. Go ahead. Now, even though matter are electrically neutral, there is a possibility of making those atoms or those substances to be charged as well. So because we say that if an object has more protons than electrons, basically the outcome would be the proton cancels out with the electron, and the outcome is basically proton. So you can actually charge a substance with adding electron or proton to it. Now there's three ways actually you can add it. Now the first way is basically called charging by contact. Okay, so basically charging by contact. Now all it means is that by contact means when you are touching it or you are making in contact with the other substance, it's basically charging by contact. Now if you have fur and if you rub the metal, what happens is you will feel the shock in it. Okay, so when you feel the shock, you're basically rubbing the metal into that fur. So all you're doing is charging that substance, charging the metal by contact. So that's basically what it means. Now what it means is that touching a charged object that can charge other object is what basically is charging by contact means. Now the second thing, okay, is basically what we said is charging by long distance. Now if you charge an object with large distance, what the term is used is basically charging by induction. So let me go ahead and erase this and talk about charging by induction. Now when you charge something by induction, you're basically charging a substance to another substance without making in contact with each other. Now the good example for that is basically during thunderstorms, negative charged particles build up in the clouds, okay, and they charge by friction. The friction charges them, okay. However, these clouds are heavy and low. The strong negative charges build up within the cloud that repel the electrons from the ground, okay. Whenever the clouds come to the near the ground, what happens is the cloud is having negative charged particle, and when it comes near the ground has negative charged particles and the positive ones, okay. And what happens, it repels this one, it takes away this one, this neutron over here. What it does, it attracts this one. So let me use the black marker to represent that this is being attracted. So negative particle is attracting the positive particle, and when negative particle is repelling the negative particle, okay, what the term that we use is basically what's called local. Okay, so local is what is used for when electron is repelling electron, and when that happens, it results in lightning. Okay, so after it's done, the process is over, the lightning strikes. Okay, so that's basically charging by induction. Now, induction, we said that charge an object without directly touching it. Okay. So we say that the local over here, negative particle repels the negative particle and attracts the positive particle, which is proton. So the electron in the clouds are basically very heavy and they're low. Okay, so the electron in the cloud basically attracts the proton, which is on the ground, and it repels the electron on the ground, which basically, when it does that, that procedure is basically called local. Now, the third thing that we'll say in this is basically what's charge polarization. Now, charge polarization is basically simple, because when you have a substance which basically has positive and negative charge at the end, okay, and the good example for that would be a magnet. Okay, so when you have a magnet, you have negative charge over here and positive charge over here. The other good example is basically water. So this is basically the water here, okay, and if this is the end point, there's negative over here and proton over here. So when you have proton located at the starting point, and when you have electron located at the ending point, starting point, ending point. Okay, so when you have proton at the starting and electron at the ending point, basically it means that it's a charge polarization. It's already a charged particle. Okay, so let's move on. Now what we are moving on is to electric fields. Electric fields. Now the space surrounding the charged object or particle or substance containing that electric field. Like we said for the gravitational field, if heavy the mass is, there is more electrical field. Same with the substance, which when it has more charge, all it means that it has more electrical charge field. Now once again, this is comparing it to the gravity, and the field basically Isaac Newton came up with the word field, which basically what I said, when you have basically more mass, results to more gravitational field. Okay, and that is what we talked about in fundamental physics. Okay, and here that is Newton's. Okay, so now we are talking actually about electrical fields, right? So for the electrical fields, if you have more charge, that results to more electric fields. Okay, and we can actually calculate the electrical fields by using the equation which basically said E is equal to the force divided by Q. Now basically E represents the electric field over here, so electric field represents this, and force, which we already talked about, the equation of the force, and Q represents the amount of charge, so amount of charge is what Q represents. Now we can actually make changes in this equation by saying that the force, which we said is equal to the K times Q1 times Q2 divided by the radius, which is squared. So what we can say is basically this. Let me just erase this over here and make changes to this equation. E, which is electric field. Force, we can replace force with saying and that divided by the amount of charge. Okay, that's basically it. But it turns out that when you have this over here, it cancels out with Q2 over here, okay, because it's the second unit over here, okay. Now what you're left is with electrical field is equal to K times Q1 divided by the radius, which is squared. Now in some cases, in some problems, they might just give you the charge of the particle, and the distance of how much the distance should be of that particle, and you need to find the electric field of that. So basically you use this equation when you need to do that, and this is basically the real equation from which we made changes. So knowing that, let's actually learn how this equation is being used in a problem. So the problem says that if the electrical field produced by an object which has a charge, so let me just erase this first. So it says that the electrical field is produced by an object which has a charge of 6.7 times 10 raised to the negative fourth, and the distance which is given us that 0.0034 meters. Okay, now, and we need to find the electric field of this. Now we already know the equation which says electrical field is basically equal to K times the Q1 divided by the radius, which is squared. Okay, now you know the value of K, which is 9.0 times 10 raised to 9 times the charged particle, which is 6.7 times 10 raised to negative 4, and you divide that by the distance, which is 0.0034 squared. So when you do that, you would get your electric field to be 5.22 times 10 raised to 11. Okay, and the units are basically Newton per Columbus. Okay, now since we know how to calculate this, the charges here are basically natural, which is being distributed themselves in the way the electric fields are always going to be zero. In other words, okay, the charges will naturally distribute this particles over here, okay, in such a way that the electric field would result in zero value. So the last thing that we'll talk about in this section over here is basically about electric potential energy and electric potential. And like I said, when I say electric potential, it doesn't mean electric potential energy, because these two concepts are both different concepts. So just as an object with a mass found in gravitational field, we talked about, with the gravitational potential energy, so when an object is standing, or when you're comparing an object standing in a gravitational field, it has some gravitational potential energy in it. So does the electric charge, which is an electric field. It has some electric charge in it, electric potential energy in it. So now we said, and I introduced you to electric potential energy. So let's go ahead and actually learn the example of that electric potential energy. But before moving on to example part, let me just introduce you to the symbols that are being used in the equation. So basically, the symbols that we'll be using in the electric potential energy, and the electric energy is basically what we write V. Okay, now V is equal to electric potential energy divided by Q. Okay, Q we know is the charge. EPE basically represents electric potential energy. Now this over here is basically watt. Okay, and it's the nice thing about electric potential energy or voltage. You can also say the watt as a voltage, and it's determining the definite value whether a charge is actually located at the position in the electric field or it's not. Okay, so basically use this equation to find the voltage of something. Okay, this is why the equation is made for. If you know the electric potential energy of a particle or charge of a substance, and if you know the charge of the substance, you basically, what you do is this electric potential energy would basically be joules, and the charge you get would be in, okay, it's Columbus. So when you have joules per, this result in voltage. Okay, now in my next video I'll be solving some examples. Okay, thank you for watching.